Alright, here is the video on non-uniform circular motion, which sounds more complicated but covers some concepts we need before the uniform circular motion or in addition to. God. Alright, anyway, let's just get to it. I'm recording this after the center of mass video. Probably should have recorded before. Doesn't really matter what order you're watching in. Well, I recommend watching this first. I'll probably indicate such. But let's get to it. So, by angular position, so circular motion is we're moving in a circle. So, whoop, wheels on a tire, centrifuge, stuff like that. And so our angular position we can get by, let's see, careful not to trip over my words. So the angular position is just theta. It's just the angle with respect to the center of our circular motion. And then if we want the arc length, the distance actually traveled, you may remember that is our radius times theta, where theta is in radians. Radians is actually, I don't know, you can imagine bending the radius on the circle. That's a radian, but and that means we don't have to do any other conversions. And that should make sense. So we go around the whole circle, one revolution is 360 degrees, 2 pi radians, and then our entire length that we traveled, the whole length of the circle, is then 2 pi for theta times r. So 2 pi r, circumference of a circle. So then we can reintroduce kind of all the concepts that we had in linear motion with angular motion. So our angular velocity, our angular position, is just the angle with respect to the center. Then our angular velocity would be the change in that angular position over change in time. So we go from a theta f to a theta I. We go from an initial theta, so this line here, to a final theta up here, and we get the angular velocity. And then just based on our definition of how we oriented our Cartesian coordinates, x, y, then it's going to be positive for counterclockwise, kind of increasing theta, and positive for counterclockwise, where our theta is increasing, and negative for clockwise, where our theta is decreasing. And in a way, getting this stuff shouldn't be as hard, because it's just so our angular velocity is the derivative of our angular position, and then the integral of our angular position is the integral of our angular velocity is is going to give us our angular distance. No, that's not quite right. Hopefully, alright, yeah, muddling my words again, but yeah, if we have an non-constant angular velocity, we can get how much we've changed by integrating it over time and adding that to our initial thing. And then if it's constant, that simplifies to theta f is equal to theta I plus angular velocity times time. So, same old equation. So then, how many revolutions does the wheel make in the first 4 seconds? We could turn this into a formula. So we slope of 1 revolution per second, integrate that over 2 seconds, but we don't really have to. We can count squares. We can do 1/2 square plus 1/2 square plus 1 square, 2 squares for the time when we're accelerating, and then 4 more squares these squares are 1 by 1, giving us 6 revolutions. Because our unit over here is revolution per second, every square is 1 revolution. So it's 1 revolution per second times 1 second. Yeah, what the heck? I'll give you, show you how to do it with Formula 2, since that's something you guys could use. I was thinking of skipping or just doing the squares method, but this is actually an instructive example since some of you had trouble in the test. Sometimes we can't solve a problem we can't write just one formula for a problem. Sometimes there's going to be a discontinuity where something changes that we can't account for with a single formula. So in this case, for between 1 and 2 seconds, we're going to have a linear equation for our angular velocity. So we should be able to see that that's a slope of 1 starting at the origin. So for that, it's just t. It's like y equals mx plus b, y equals, this is equal to, got slope of 1, and we start at the origin. So we just have this relationship with our units. And that's between t, when t is less than or equal to 2 seconds and greater than or equal to 0 seconds. Then at 2 seconds, we have another formula, very simple one, but it does have to change, where it just stays at 2. That's the wrong direction. When t is greater than 2. And so we can combine these two, and we need to go for 4 seconds. So if we're integrating this over time, which is what we did manually by counting squares, then we have integral from 4 to 0 t, but then we have to split it because it's 2 different equations. So we'll go from 2 to 0 of just t, dt, forgot over here, dt, and then plus, hold on, working with my tablet. Alright, plus integral from 4 to 2 of just 2 dt. Is that right? Hold on. Yeah, that's right. So, solving those, we get, so t squared over 2 from 2 to 0 plus 2t from 4 to 2. I'm not going to write all this out, but so this would be 4 halves minus 0, so 2, like the 2 squares we found. Then this would be 8 minus 4, so the 4 more squares we found, and our answer is 4. So, not that complicated, but I figured the process of breaking the integral down into these 2 sections was worth going over and proving to you that that's the correct answer. Alright, let's get back to this. Alright, and so we introduced the concept of a period. A period is the amount of time it takes to go 1 rotation, and therefore our speed is the radians of a full rotation, 2 pi, divided by our period, and then we get that inverse relationship as well. We do have to absolute value because we could be going clockwise instead of counterclockwise. Period doesn't tell us which direction we're going. So a ball rolls around a circular track with an angle. What is its period? Just look at our formula. So we take our 2 pi divided by angular velocity. That's 1/2 seconds. So we're moving 2 times around the track in 1 second, or we're moving around the track in half a second. And then, so if we want to relate to this back to the same way, we could get our arc length by multiplying theta by r. We can get our velocity, our tangential velocity, which we'll explain a bit, by multiplying our angular velocity by r. And that's, you might think, why are we doing this? It's because sometimes it's going to be useful to have a real velocity or a linear velocity. Sometimes it's going to be useful to have an angular velocity when objects are interacting, like so. So if you're on the merry-go-round, you have what is your angular velocity between these two people on the same merry-go-round at different distances. It's the same, because even though they're traveling different distances, linear distances, they're traveling the same angle in the same amount of time. But if we want, so if Sophia is twice as far as Rashid, then we have to add in that r factor twice. So his radius, or Sophia's radius, is twice that of Rashid. God, names, Rashid, and therefore his tangential velocity is twice hers. And we can see he's moving in like a wider circle in the same amount of time. He's got to be going faster from our linear perspective. By the way, I guess it's worth mentioning when we say tangential velocity, might be some problems with it later. Let's see, I need a pen online, but tangential velocity is basically, you would think if all of a sudden she fell off the merry-go-round, that's the direction she'd go flying from the existing angular velocity, so that's another way of thinking of it. Alright, so we've done velocity and position. What do we think we're doing next? We're doing acceleration. Shocking, I know, but then everything, once again, we're going through the same process. Angular acceleration is the differential of angular velocity with respect to time, or the double derivative of angular position with respect to time. Same process. And we want to think of it, it's the amount that the angular velocity is increasing or decreasing, and then and it could be, there's all these different positions. So yeah, so the top line is how it started. So if we're speeding up, going counterclockwise, then the angular velocity is positive, the angular acceleration is positive. So we're starting out going this direction, and then we're going even faster this direction as we kind of crank up the rotation. Then if our angular velocity is positive and our acceleration is negative, we're going this way and we're slowing down until we eventually turn around and start rotating the other direction. Likewise, this is negative, this is positive. We're slowing down as we rotate in this direction. If this is negative, this is positive, or if they're both negative, then we're now accelerating in the clockwise direction. What do we have left? And yep, so we can reassemble all our usual formulas based on these all these come from derivative properties. I think I have a video explaining that. So they all work for this scenario as well. How much time? One more example. The fan blade is slowing down. What are the signs? Okay, you can just correlate. Anything else I want to go over? I think these shouldn't be too hard. It's all definitional. Yep,